Alright, this tutorial video is all about dilations. And the key concept about a dilation is that you have some center of dilation, in this case point T, and look at the letters that indicate the points. Notice how one of them does not have a prime and one of them does have a prime. That means this one is sort of the original or the pre-image. And this one with the prime is sort of like the new one called the image. So, but think of it like you had this original point and then somehow it became this new point. So the idea of dilations, though, is that the original point was a certain distance from the center of dilation. And in this case, that distance was 8, 2 plus 6. So we had this original distance of 8. And then the new point, x prime, is some new distance from point T. And that is 6. So think of it that way. That's what's happening. So sometimes we talk about something called the scale factor. Okay, and I'm going to use the letter K to represent the scale factor. The scale factor is always going to be the new distance divided by the old distance. So for this problem, the scale factor would be, let's see, the new distance is the 6 because of the x prime, and the old distance is 8. So that means the scale factor, if I reduce this, is 3/4. Now we don't really need that exactly for this particular problem, but you should know what scale factor is. Now for this problem, probably the easiest way to look at it is thinking about similar triangles. So when you do a dilation like this, you're often going to get these similar triangles. Looking at the big triangle that reaches out to those original points, x and y, that's one of the triangles I'm talking about. But then here's the smaller triangle reaching out to x prime and y prime. So this larger blue triangle and the smaller pink triangle, these are similar triangles. Now that's going to be helpful because the corresponding sides are going to be proportional, meaning the ratios should be the same if we start making fractions out of them. So for example, if you look at a side of the big triangle, so here's a side of the big triangle, this side has length 8, 2 plus 6. And then of course the corresponding side of the smaller triangle right here is just the 6. So I could make a ratio out of that if I wanted to. It doesn't matter if I go big over small or if I go small over big. All right, but I'm gonna go big over small. So that would be 8 over 6. Okay, now if I have another ratio, another pair of sides of the triangles, I could make another fraction. So let's look at this side over here. So this small side right here is of course 9 because it's right there. Now the larger side, the corresponding side of the larger triangle, we don't know what that is. I'm going to call it x, but that's what we're supposed to find. We're supposed to find yt. So if we find x, then that's what we found is yt. So we can just make another fraction. Again, we were doing big over small for this pair of sides, so I'm going to do that again. So the big side here is x, and the small side is 9. So big over small should equal big over small. Now notice I'm talking about entire sides of the triangle. I couldn't make a fraction out of 2 and 6 because 2 is not a side of the triangle. 2 is just this little tiny piece of a side. So it's important that when you're building these fractions, you're using entire sides of triangles. Small side of a triangle, big side of a triangle. Corresponding small side of a triangle, big side of a triangle. So these are proportional, so they should be equal. So now it's just a matter of solving this equation. So I have x over 9. 8 over 6 reduces down to 4 over 3. And if I want to get x by itself, the easiest thing to do would be just to multiply by 9 on both sides. So those 9s would cancel each other out. Okay, so now I have x is equal to 4 times 9 is 36. Alright, because this is like 9 over 1. So I have 36 over 3. And 36 divided by 3 is 12. So this should be the answer right here. And there you go. Okay, now looking at this problem, alright, it's pretty similar, but this time they just want to know what is the scale factor. So I'm going to use the letter K to represent the scale factor. Remember that K is going to be, the scale factor is going to be the new distance divided by the old distance. Okay, new divided by old. So be careful to look for the prime. When you see the prime, you know that's going to be the new point. So when I see this 3.2, okay, that's the distance from the center to V prime. I know that's the new distance. So I'm going to put that on the top, 3.2. Now here's the V without the prime. So I know that this distance must be the old distance, the original distance. So be careful, this distance is not 4.8. Alright, 4.8 is just between V prime and V. I need the entire distance. I need 3.2 plus 4.8. So that distance is 8. Okay, so new over old, that's 3.2 divided by 8. If you put that in your, okay, 3.2 divided by 8 is 0.4. Now on my TI-30XS multiview, if I hit this button, that's going to turn it into a fraction for me, 2/5. Notice if I did the fraction in the first place and did 3.2 over 8, you know what, that's still, I guess either way, I thought it was going to just give me the fraction, but either way I have to hit my toggle key. So anyway, the fraction is 2/5. So that is my scale factor. So there it is right there at the top. And there you go. Okay, so we have this dilation happening. Apparently the scale factor is 1/3, because that's what this means. The image triangle J prime, K prime, L prime is the result of the dilation. So that means that this is basically the old triangle, the pre-image, and this is the new triangle, the image. Okay, so what is L prime? So here is L prime right here, this distance right here. So I'm going to go ahead and put an X right here to indicate that this is what we're looking for. Now, what we have to go on is the scale factor, which is 1/3. So remember, the scale factor, which I'm going to call K, works like this. The scale factor is always going to equal the new distance divided by the old distance. So the scale factor is 1/3. So that means 1/3 should equal the new distance divided by the old distance. So let's see. This is the new distance right here because you see the L prime. So the new distance is this 2.5. Now the old distance is the distance to the L without the prime. So this is the old distance right here. Notice that the old distance is not simply x. It's this entire distance from M to L. X is just the distance between the L's. So I don't actually know the entire distance from M to L, but I can make an expression because this entire distance should be the 2.5 plus the x together. So I'll go ahead and write that as x plus 2.5 because we usually put the variable first. Alright, but it's the sum of these two. That's the old distance. So that's what I have to put into this fraction. So the new distance was 2.5. So I'll put that in the top. The old distance was x plus 2.5. So I'm going to put that in the bottom. So it's a matter of solving this equation. So I'm going to do something that is called cross multiplying. That's where you can take one diagonal, multiply that together, and put that on the left side. So 1 times x plus 2.5 is just going to be x plus 2.5, since multiplying by 1 doesn't really change anything. And that should equal, now I'm going to do the other diagonal. Okay, so I'm going to do 3 times 2.5. Alright, I'm just going to punch that in my calculator real quick. So 3 times 2.5 is 7.5. Okay, so obviously to solve this, all I need to do is subtract 2.5 from both sides. Okay, so that should equal 5. So that means that this should be the answer to the question right here at the top. And there you go. Okay, the perimeter of triangle ABC is 13. It was dilated to create the triangle A prime, B prime, C prime. The perimeter of triangle is, I feel like they're missing some words here, but I think it's pretty clear that they mean what's the perimeter of the new triangle, A prime, B prime, C prime, since we already know the perimeter of the small triangle. So let's see, let's talk in terms of new and old. So ABC was the original triangle, that's why it's called ABC. Alright, the primes, that's the new one. So the old triangle, alright, had perimeter of 13. And then now we want the perimeter of the new triangle. Okay, and I'll call that perimeter prime. Alright, that's what we're looking for. So let's see. It would be helpful if we had the scale factor for this problem. So remember how the scale factor works. The scale factor, which I'm going to call K, is always a new distance divided by the old distance. Okay? So the new distance would be the distance from O all the way to B prime. Alright, because the prime, that's the new. So this is the new distance. Okay, and that is not 15, it is 20. Alright, it's the 5 plus the 15. That's the new distance. Alright, so that would go in the top. Now the old distance is going to be the distance to the b without the prime. So this is the old distance right here, which is clearly 5. So the scale factor then is 20 divided by 5, which is just 4. So that's the scale factor. Now, we can use the scale factor with the perimeters as well. Alright, so let's go back to what we said a minute ago. The scale factor is going to always equal the new divided by the old. Alright, but that works with perimeters too. So the scale factor should equal the new perimeter, which I'll call P prime, divided by the old perimeter. Okay, let me move this equation over here. So the scale factor should equal the new perimeter divided by the old perimeter. Alright, the new perimeter, that's what we're trying to find. Alright, now the old perimeter we know is 13. Alright, and the scale factor k, we already found it. We know that it's 4. Alright, so the scale factor should equal the new perimeter divided by the old perimeter. So we have this equation, which is easy to solve. So all we need to do is multiply both sides by 13. Okay, so 13 times 4. So that's 52. Alright, so that should be the new perimeter. Let's check it out. Alright, that's why the new perimeter should be 52. Okay, so Jeremy wants to verify that the transformation shown is a dilation. He finds the lengths of segments QA and segments AD to both be 4 units. Now, to verify the transformation is a dilation, Jeremy should also check which of the following. Check all that apply. So basically they're asking us which of these should be true if this is a dilation. Okay, so now the key concept behind a dilation is the idea of a scale factor. So remember that the idea of the scale factor is all about that if you take any ratio and you do new divided by old corresponding lengths, they should always be equal. Alright? Any new distance or length divided by the old distance or length should always equal the scale factor. So if we figure out what the scale factor is, that should help us see which of these would have to be true. So, okay, so this time they didn't give us primes or anything, so it's up to us to decide and just pick which one we're gonna think of as the new and which one we will think of as the old. So I'm gonna just choose to think of this one as the original triangle, and I'm gonna think of this one as the new triangle. Okay, so if I look at it that way, then this is the original distance of 4, and then the new distance after the dilation, alright, is 4 plus 4, which is 8. So that would mean my scale factor, which is new distance over old distance, is going to be 8 over 4, which is 2. Okay, so since the scale factor is 2, in other words, new over old equals 2, basically that means that the new triangle is twice as big as the old triangle, or any new distance is going to be twice as big as the old distance. Alright, so let me just write it that way. So, alright, another way of looking at this is that any new distance is going to be twice as big as the old distance. Or if I flip it the other way around, any old distance should be half the size of the new distance. All right, see how we have the old triangle was small and the new triangle is big? So the old triangle is half the size of the new triangle. Or the new triangle is twice as big as the old triangle. Those two things basically mean the same thing. So if I look at, for example, this first statement to see if it should be true. QB is equal to 1/2 QE. Well, let's see. Now QB, that is an old distance. All right, and then QE is a corresponding new distance. So the old distance should be half the size of this new distance. So QB should equal half the size of QE. So that does make sense. All right, next we're going to look at QC and CF. Now QC is right here. All right, that is an old distance, but the thing that we have next is really something quite different. CF is not the new distance. Sorry, the new distance would have been all the way from Q to F. So we just have these two pieces. Now this is very similar to what we looked at the very beginning when we had the 4 and the other 4. See how these are equal? Now that should happen down here again. These should be equal again. But that's because the new distance has got to be twice as big as the old distance. For example, if the new distance, let's just imagine that it was 10. All right, that's the new distance, would be the whole thing. Then that would mean that the old distance would be half the size of that, which would be 5. But then wait a minute, what would that leave for this other piece over here? Well, that would also be 5. So that's always going to happen. If the bigger distance is twice as big as the smaller distance, then the two pieces are going to be equal to each other. So just like the 4 equals to 4, QC should always equal CF. So that should be also true. Okay, what else? Let's look at DE and DE and AB. How do they compare? Erase some of this stuff. Okay, so DE. DE is a new distance. All right, it's one of the sides of this triangle. That's a new length. What about AB? AB is a corresponding side of the old triangle. Okay, so let's see, which one do they say first? They say DE first. So the new triangle, the new side, should be twice as big as the old side. So this should be true. Okay, DE, the new side, should be twice as big as the old side. So that should be true. Okay, now let's look at AC and EF. Okay, where's AC? So here's AC. That is an old side. All right, so we have an old side. And then EF. I see a problem right now. Okay, so we have an old side and we have a new side, but what's wrong with these in terms of saying, oh, the new side should be twice as big as the old side or something like that? These are not corresponding sides. AC and EF do not match. If I was going to do AC, then the corresponding side for that would be DF. Okay, not EF. So because these are not corresponding sides, then we can't say anything about them. So this would not be a statement that we can know. So that should be an X. All right, let's look at the last statement. Okay, if BC is equal to 2.25, let's see, where's BC? BC, all right, so BC is an old length, which is right here, and they're saying imagine that that is 2.25, and EF will also equal 2.25. Well, that doesn't make any sense at all, does it? All right, because EF should be twice as big as BC. These are corresponding sides. The old one is 2.25. The new one should be twice as big as that. So this should be 4.5, not 2.25. Okay, so that is false. All right, let's see how we did. All right, and there you go. All right, that's the end of this tutorial video. I hope it was helpful. I hope you took notes, and go ahead and use them as you retake the quiz. Good luck.